Hello and welcome to Chapter 22, Motions in the Heavens for Finlandia University's Earth Science class. As usual, I say at the beginning of every video, if you have any questions, comment them down below or send them to me. I'll get to them when I can, or someone else in the class will proceed to try to answer your question. And let's begin talking about the motions in the heavens. As you can notice, of course, we've left the Earth essentially and gone beyond, because this is an Earth science class, right? This is not a class on strictly geology. We started with geology, but we segued into the hydrosphere, then the atmosphere, and now in the solar system. So, motions of the heavenly bodies, very antiquated way of saying it, right? Well, you'll come to see. The sun and the moon rise in the east, set in the west. Well established, well understood, right? Stars remain more or less fixed in the sky relative to one another. We call the groups of stars constellations because they arguably resemble certain patterns. And then we have planets which move independent of the stars. Essentially, the stars in the sky, when you look up every night, more or less look the same. And then if you notice stars that move over a short period of time, those would be what the ancient civilizations would have called planets. I think the original words like uh, random stars, or was it moving star? I can't quite remember the phrase off the top of my head, but the planets were considered stars that moved, and the stars are considered stars that stayed in their place. Interestingly enough, some of these planets had what we call retrograde motion, or a reverse motion from what's previously been had. Well, that's interesting. Some of the stars move, some of the stars don't, and some of the stars move backwards sometimes. Ancient peoples tried to figure out what was going on with this confusion. Here we have a picture of a time exposure, or a very long photo of the stars at the North Pole. People didn't live at the North Pole, so they went to see this, but high latitude people would have seen something approximating this. And what you're looking at is the trail the star takes as the Earth spins around. Fascinating. The very first models we had for the universe and the solar system and the way everything works were geocentric models. This meant Earth-centered universe. We exist, everything moves around us. The idea being that there were these celestial spheres or concentrated layers of crystal or firmament on which stars were fixed, put into position, sort of similar to the roof of your house. People don't really have a sense of motion. So when you're standing here, so the sky must be moving and not us, right? If I stand up, it doesn't feel like I'm moved in between sitting down and standing up. Therefore, I must not have moved. People don't fall off the earth or get flung off it from the earth moving. So therefore, the stars must be moving. But you run into issues with things such as parallax. Parallax is we'll get into this with pictures, the apparent change in position of an object based on the observer's change in position. What do you do about this, right? Here is images of parallax. These posts here and these posts here seem to have a very different relationship with one another. Well, that's because I've moved relative to the posts. The posts themselves haven't moved, but I've moved. So these nearby posts that look all squished together here are in fact not squished together here. This is a very brief idea of parallax. Aristotle's geocentric model explained most of the heavenly bodies, but had a problem with things such as retrograde motion. If the sky, the night sky, essentially was like a rotating ceiling on top of the room that is the earth, how do you explain things that don't appear at the same location all the time? How do you explain things that move not only relative to each other, but backwards relative to each other, right? If the firmament, if the cover, or as I say here, the sphere of the sky is spinning, you need to explain how everything spins within that spin. Ptolemy, a astronomer in 150 AD or Common Era, accounted for its retrograde motion by using epicycles in a geocentric system. Epicycles were a very interesting approach. The idea being things usually rotate in circles, but sometimes things will rotate in circles while they circle. This very peculiar, odd motion giving you what looks like, as things go on in circle, a backwards motion sometimes as things circling around, giving you that retrograde motion that we were talking about. A nearby star appeared to change position with respect to the distance. Let me restart that, please. A nearby star appears to change position with respect to the distant stars as Earth orbits around the sun. This drawing is, well, of course, greatly exaggerated. In reality, the distance to the nearest stars is so much greater than diameter. It would be a small fraction of a distance. But this concept here is the parallax problem that old geocentric models have an issue with. During the summer, a star appears in one location. During the winter, a star appears in a different location. Again, how do we have this parallax issue resolved if the night sky is just a sphere rotating around the Earth, similar to the ceiling in your room spinning around? Well, here's your epicycle idea where the planets are rotating as they rotate around, giving you this odd retrograde, lots of motion on top of motion on top of motion to solve these problems. So many issues. What do we do about this? Well, not many people cared a whole lot for some 1400 years after Aristotle and Ptolemy proposed these theories. It really wasn't super relevant. But civilizations advanced, people got more time to study things outside of where's my next meal coming from, and up pops Copernicus. Copernicus is a Polish astronomer that found Ptolemaic systems too complicated. The idea of the sphere, the firmament, the crystal that's on top of the Earth is spinning, and then things are spinning within that spin. Everything has its own spin to account for its own way of moving around. And we have stars in different locations. That must be some adjustment of the sphere. Right? We're getting really complicated here. Is there a better solution to this? He posited the heliocentric model. Heliocentric model is what you learned about in school, where the sun is the center of the solar system and the Earth rotates around it, as opposed to what we have down here below. This accounted nicely for retrograde motion because now all the other moving objects in the sky are moving while we are moving. So similar to if you're in a car down the highway and you pass someone, they appear to you to be moving backwards, but in reality, both of you are moving forward. This easily counts for retrograde motion. Brahe, following astronomer, mapped all known objects in space, and then Kepler inherited the data from Brahe's death and posited the idea of elliptical orbits of planets. So Copernicus said, let's put the sun at the center and let's move us. Brahe said, okay, I'll chart everything that moves. And Kepler said, oh, cool. These charts say that this circular motion here maybe isn't the best way to describe it. Maybe we can do, should I have an image? Not really too well. Maybe instead of these circles, we can have elliptical motions or non-perfect circles to explain the differences in the way things move in the night sky. So we have the Earth rotating around, and we look and we notice Mars, as shown here, at these very different spots in the Earth's orbit. It's called this, January, February, March, April, May, June, July, August, something like that. Each month, the same day, you look and you find Mars, and you notice that Mars is moving in odd ways. The first day, Mars is moving out here, but in April, May, June, Mars appears to be backtracking a bit from its previous location. The elliptical explanation of Mars's motion explains this phenomenon. And this took literally 1,500 years to figure out. At first, you had to accept that Aristotle was incorrect, which was a big deal back then. And then you actually had to go through the proper scientific method of formulating a hypothesis, gathering data, testing the data, coming to a conclusion. And this work from these astronomers, writing with candles and quills, gave us the foundation of a proper modern understanding of the solar system. Galileo, big name in astronomy, right? Galileo was an astronomer, mathematician, and physicist, and he thought the laws of nature must be understood by observation, experimentation, analysis. He observed moving objects, and therefore he derived laws of motion based on his observations. Big step forward again from Aristotle, who said, well, that kind of looks like a ceiling, so I'm going to say it's a ceiling. It's a big ceiling around the Earth, and all the stars are just dots in the ceiling. Oh, this is a problem? Well, let's make up an ad hoc, make up something to explain these weird quirks. Galileo did something a little better than that, right? We can then look on to Newton, who quantified and expanded some of these laws that Galileo had, presenting ideas such as inertia, or the tendency of objects to resist a change in motion. And since the change in motion is the big thing, maybe we can have the Earth as the moving part of the solar system, because since the Earth's motion isn't changing, we're not going to notice that change. We have the same inertia that the Earth does. If the Earth changed its motion, we would notice that, but since the Earth has not changed its motion, we wouldn't expect to notice that. Things are coming together based on, as said here, observation, experimentation, and analysis. Put these pieces together. Galileo questioned the basis of Aristotelian view, and he built telescopes. He observed the seas on the moon. He observed sunspots. He observed Jupiter had moons around it, the Galilean moons, right? He observed Venus had moon-like phases. All these things that kept poking holes, breaking down that crystal sphere that was the Aristotelian view of the world at that time. In Ptolemy's theory, Aristotle's theory, Venus could never move farther from the sun than is showed by these dotted lines here. Therefore, it always appeared as a crescent. But the heliocentric view, Venus passes through phases like our moon does. Galileo observed these phases through his telescope, concluded that Venus was indeed a planet. Notice the shading on Venus in all of these examples. This is what was observed. Therefore, this theory holds ground better than this explanation that fits the model rather than fitting the observation. Venus doesn't exist with a little crescent always facing the sun. So it doesn't have these weird epicycles within its cycle. Instead, it has this elliptical orbit around the sun, as shown. Classically, you've probably heard this conversation before. The Catholic Church of the day forced Galileo to recant his heliocentric theory. He was put under house arrest. Big old thing happened about Galileo at the time. Move on in the future, you run into Isaac Newton. Isaac Newton invents calculus. He did this in like his 20s. It's nuts, right? And Newton answered why planets moved in elliptical orbits by citing the fact that, a moving body moves in a straight line unless it's acted upon by an outside force. And therefore, since the planets are not moving in straight lines, they must be acting upon by an outside force. And Newton theorized this force would be gravity. Gravity is what's pulling the planets into their rotation as they fly around. So similar to if you spin a yo-yo over your head, right? The string is what's keeping the yo-yo from flying away. Newton posited that a force similar to that is what's keeping the planets in these unique motions. And he posited this because he noticed the planets had these unique motions. And his understanding of the data led him to a theory that is more or less still what we work with today with our satellites and rockets and what have you. By about 1700, heroes say, the heliocentric system was well established. Most people in the world understood that the Earth is the center of the solar system, we revolve around it, and everything else moves in accordance. This gives us ideas such as rotation, revolution, and precession. Rotation would be the object spinning on its axis. This is our day-night cycle. Revolution is the object moving around. This would be our season cycle in the year. And precession would be the non-uniform motion of that rotation, or well, I guess even that revolution. As usual, I don't go over these questions, but I will stop here in case you want to pause and answer it, because if you can answer these questions, you're doing pretty well with this subject. The night sky changes with seasons. This is because the Earth is essentially looking at different things at different times. If you look at the night sky, if you look at a particular region of the night sky, say in the fall, and then you look at that same part of night sky 6 months later, say in the spring, you will notice that you are looking at slightly different pictures. And this is due, again, to the fact that where you're looking is slightly different locations. Furthermore, we can talk the precession, similar again shown here to a wobbling top, where you look isn't always going to be in the same location. The North Star is currently the star that's above the North Pole, but given the precession and the wobble of the Earth, again, similar to the wobble of a top, the North Star has not always been the star that's above the North Pole. As the Earth wobbles back and forth some 23.5 degrees, time in the past, Vega was actually the star that showed up for the North Pole. And that's very interesting. Old star maps are inaccurate because the Earth moves, the Earth changes the way it moves as it travels throughout the solar system, the universe, the galaxy, what have you. All right, let's talk about the moon a little bit. Hopefully that super brief dive into astronomy set you up for a deeper dive into the moon. The moon revolves on the Earth every 29.5 days. The look of the moon has many different names to it: new moon, crescent, gibbous, full, waning, what have you. We call it a new moon when the moon is very dark. 4 days from this, we hit crescent moons until eventually we cycle into a gibbous moon, which is a bright moon, some 10 days later, and then eventually a full moon. The full moon is some 14 days or about halfway through the revolution of the moon. This is our big, bright full moon, right? You know what a full moon is. And then as the moon reverses this trend, we call that a waning moon. You've seen all these up in the night sky before, right? This moon cycle is another example of the revolution and rotation involved with the night sky. Although rotations, it's another can of worms for this conversation, right? And before we go on to the next slides, try to stop, pause the video if you want, and think about why would the moon have these shadows growing and receding throughout its revolution of the Earth? Why, when the moon is in this part of its revolution, does it look like this, but when it's in this part of the revolution, it looks like this? Because the shadow appears to be moving away to the left and then adding itself back in again from the left. Why is that? The full moon. Full moon rises at about sunset each night. It takes about 53 minutes. And, well, it looks like it's very bright in the night sky, right? The moon is actually not emitting any light. At this point, the moon is reflecting solar light. Hint, hint as to why it works this way, right? Here we have an example of why the moon goes through these cycles. And this, again, is very interesting. The new moon happens when the moon is in between the Earth and the sun. Not eclipse, we'll get to that in a bit, but when the moon's cycle is in between the Earth and the sun for nighttime, such that all the sunlight of the moon hits the side we don't see. We are looking at the shadow of the moon during a new moon. And given the 5.2 degree plane that the moon orbits, the moon doesn't just orbit flat with the Earth, it moves at a bit of a plane. As it cycles around to a full moon, we get the opposite effect here, where the Earth is before the moon, but a 5.2 degree difference between them means that you don't necessarily run into an issue of an eclipse because the Earth's shadow is not connecting with the moon shadow, giving us this full bright moon look like we have here. Because the sun sits over here. Let's say the sun's over here beyond the new moon. Look here. And it's shining its light this way. But this image in the center is not completely accurate because you got to kind of do a 3D sort of movement of that moon disk so that it's not parallel with the Earth. Instead, it's at an angle with the Earth. It's hard to show in 2D. I can understand the confusion here. This intersecting planes as shown here. But this is what gives us this very fun interaction between the moon and the Earth. Of course, scales are exaggerated for emphasis as shown here, but I hope the concept's getting across, right? The moon and the Earth have a relationship such that the shadows made by them the vast majority of the time are not interacting. Unless, of course, the shadows do interact, in which case we have an eclipse. You've all seen an eclipse before. They're not uncommon, but they're also not rare, right? You'll see many of them in your lifetime. The eclipses of the sun and the moon come in two forms: solar eclipses and lunar eclipses. A solar eclipse happens when the moon passes directly between the sun and the Earth. Again, you need to remember that the motions of these bodies are not as simple as what appears in posters and what have you. They have very complex interactions at different angles, at different speeds, rotations, revolutions, what have you. So when the moon passes in such a way that's directly between the sun and the Earth, accounting for that 5.2% difference, we have a solar eclipse where we have an umbra and a penumbra happening. A region of shadow exhibiting the total eclipse is the umbra, as shown, where am I at? Here. This is the moon is, this is the example you get where the sun is just outlying the moon. This is your umbra. And then you also have your penumbra, which is the edge of the shadow showing the partial eclipse. This is where instead of getting that nice little edge or full coverage of the sun, you get majority coverage of the sun. The entire world at that time sees the eclipse, but if you remember if you watch the news, something like that, I tell you where you can get the best eclipse, and it's this little streak going across the Earth. That little streak is actually the umbra of the moon, and you only get those in places the width of the shadow here, right? Interesting concepts. And that's due, again, to a correct connection between this 5.2 degree angle, the timing of the new moon rolling around, and the Earth-Sun relationship. Astronomy is a complicated subject, isn't it? Of course, we can also have lunar eclipses. This is when the Earth lies between the moon and the sun, and they last longer, far more common because the Earth is bigger and casts a bigger shadow, right? Here's your new moon, full moon conversation where the shadows are not mixing. And then here are examples of solar and lunar eclipses. Somehow I forgot that word, where the moon is between the Earth and the sun, causing that umbra there, or the Earth is between the moon and the sun, causing the moon itself to not get any sunlight. And these pictures always upset me because it kind of looks like they're sitting on grass for some reason. That's always been really confusing to me. Cool. Moon's complicated. All this stuff is complicated. Hopefully I'm enlightening you a little bit on these processes. Lastly, let's talk about tools. Modern astronomy. Human eyes aren't very good for studying the solar system, right? Aristotle did the best he could with his eyes, but you can only get so much out of it. Galileo built a telescope in order to find out that Aristotle's view of things with just his eyes were inaccurate. And today we have bigger and better and stronger and more powerful telescopes that tell us much more about the solar system than we've ever known before. Optical telescopes being the most common telescope that you think of when you think of a telescope. These are devices that collect the light from a wide area and focus into a narrow area for our detection. Refracting telescopes include telescopes that have two lenses and a tube, usually with an objective, not usually, always with an objective lens that is larger than the seeing eye, an eyepiece to look into, and a bending of the light into its location, giving you upside down, funny enough, images, but it's a star. You don't care that it's upside down, right? This is a refracting telescope, is a telescope that you think of when you picture a telescope. A big long tube with some big pieces of glass in the middle of it. A reflecting telescope is another variation that instead of refracting light, as shown here, reflects it via a secondary mirror. Reflecting versus refracting telescope is a whole conversation of itself as to which is better. My suggestion to you is get a telescope. They're cool either way, right? But there's also a third type of telescope we're not going to cover here, but you can actually make your own telescope if you want. Comment down below if you want some hints to how to do that. Astronomy is a fantastic hobby to get into. A little bit of a price of introductory in order to buy the telescope, and then you essentially have fully paid for the entire hobby. It's really cool stuff. But anyways, to go back to human eyes at poor resolution, here's an example of resolution that's helpful. A big old blob is in fact two separate stars. You understood that. I hope you did. Yeah, here's your reflecting telescope, which is this guy here. In general, I guess the pros and cons would be these guys are simpler and more common. These guys, the reflecting telescopes, you tend to get more magnification for less space because this travel time is double. Sorry, actually, it's not the travel time. This area here can be larger to accept more light than this guy without having to expand this circle around, because all this light needs to be collected and then brought down to your eyepiece here. So everything needs to be pinched in. Whereas this guy, they can all be pinched in, not to the eyepiece size, but to a mirror here in the center. But yeah, beyond the telescopes you could own, of course, we have telescopes as satellites. The most famous of these would naturally be the Hubble Space Telescope. Why would we put a telescope up in space? Well, mostly light pollution and the atmosphere, of course. If you live in a city, you will notice that the nighttime sky isn't as bright because the light of the city, the light of the area that you live in, is fighting with the light of the sky. commonly a astronomer is going to go. Astronomy stations on Earth are tops of mountains, isolated areas, because you don't want to have to deal with street lights, cars, highways, what have you, buildings, providing more background light than the stars you actually want to look at. Telescopes in Hawaii are mostly above these light pollution problems. And of course, you also have issues of the atmosphere and reflection of the light from the heavens. But again, that's going more in depth than needs to be for this introductory conversation. Image of the Hubble Space Telescope is, of course, is a reconstruction, not an actual Polaroid. But the Hubble Space Telescope allows us to take pictures of a universe on a before then unimaginably detailed scale. This is an actual picture you're looking at. This is not an artist's rendition like this is. That's an image that the Hubble Space Telescope took in more or less the same way that you would take with a telescope in your backyard. The Hubble Space Telescope, however, has the advantage of being big and not having to deal with city street lights, not having to deal with cloudy days, not having to deal with any of that information. And telescopes can be used again. Look at this thing, a 10-meter mirror of a telescope is comprised of 36 separate hexagonal sections that are adjusted by a computer to achieve the images that you want. This view shows the mirror under construction, of course, 18 of its sections installed right here, those 18 hexagons. This worker is teeny compared to the gigantic size of this mirror. And this is how we get these fascinating images. And this information from telescopes like Hubble and others provide us with the expansive knowledge of the universe that we currently have. Of course, those are visual telescopes, right? Those are in the EM spectrum, the visible light spectrum. That's what these guys mostly deal with. However, we can look other parts of the EM spectrum and find out other interesting information. There exist radio telescopes that capture radio signals from outer space and decipher that information. X-ray telescopes, infrared telescopes, gamma ray instruments. Each of these different wavelengths can provide us with fascinating information on whatever we're looking at. The makeup of stars, the distance of galaxies, exploding supernovas, gravitational waves, what have you. This stuff is all understood in the vast array that is astronomy. As said before, something else we can discuss are emission and absorption spectrums. We can know what elements are in stars hundreds of light years away, given these very exciting forms of scientific inquiry. A spectrum, in case you are unaware in the terminology that we're talking about here, is an ordered array of colors exhibited by light diverging through a prism. Picture the Dark Side of the Moon album cover of Pink Floyd, if you will. And the absorption spectrum are the atoms in a star's exterior that absorb certain wavelengths, creating a pattern of absorption bands. And the spectra then is produced by this absorption emission conversation. And what this kind of boils down to is certain elements like give off certain colors of light. You may have done this in a physics lab before, where you take a nitrogen, a vial with electrodes in it that contains nitrogen, you plug that in, and that particular vial glows a certain color. And then you replace that with a different color, say carbon dioxide, and that again glows a certain color. A halogen light is those big, long, thin lights that you put up like in construction areas. Those just have a gas running through them. And when you run electricity through that gas, it exhibits that blinding white light, right? Going to Walmart. That's the kind of light I'm talking about here. And this information that different elements produce different colors when you run electricity through them allows us to look at the emission or the light that is given out by these various things out in space, these various stars, planets, what have you, and allows us to kind of understand how stars are created, how planets are created, things like that. And it's truly fascinating that I can point to any particular star in the sky and with the correct instrument tell you what elements are made up of that star. And then I can take the information, compile it with other information, tell you how old that star is, tell you how big that star is, tell you how many planets are around that star, tell you how far away that star is, etc., etc., etc. Fascinating stuff, right? Oh, well, there's your Dark Side of the Moon cover. Where here, these are the spectrum lines that we were talking about earlier. The gaps in this prism, the gaps in this emission spectra shown here are indicative of certain elements that are blocking those particular wavelengths of light from being released. And again, if you go back to, you may have done it in high school physics class, I'm unaware, but you can just look at the example of, again, the halogen lights from when you go into Walmart. That particular light is unique, right? That color of light is different from, say, the headlights in your car, or say the LED lights that you probably hopefully have in your house now. Those are different types of light, and because there's different reasons they're being produced. I don't want to I'm getting off topic into emission spectra a bit more than I should. It's really cool. It's fascinating. Comment down below if you'd like some more information. I can hopefully lead you in a direction that is beneficial. Let's finish up by talking about Doppler measurements. You look up in space, you can see things move like left to right, up and down, but how can you tell things move back and forth? The third dimension, right? Lucky for us, especially when it comes to stars, we can look at what's called red shifting and blue shifting. And this is, you're familiar with the Doppler effect, I'm sure. When a police car, an ambulance goes by you, you hear it, wee wee wee, right? It gets higher pitch as it comes towards you and lower pitched as it drives away. Funny enough, light does a very similar thing for basically the same reason. If a star, for example, is giving off light and that star is moving away from us, we will have a lengthening of the light that the star has been given off via the Doppler effect shown here. What that lengthening does is it essentially changes the wavelength of the light that it hits us, causing it to move towards the red spectrum of the visible light spectrum. And if it's moving closer to us, it's bluer looking light. So when you look up at a night sky and you see a blue star, that star is actually coming at you. It's fascinating stuff, right? Light behaves in a very similar way to sound in that regard. And this information allows us to then expand upon, well, the expansion of the galaxy, space-time, all these other ridiculous concepts Aristotle couldn't have dreamt about in his wildest imagination. We have data and numbers and statistics and models to verify vast depths and reaches of the solar system. So I went off on a bit of a tangent there, but astronomy is a very cool thing, right? There's a whole lot to unpack in this topic, much more than, sadly, the 3 chapters I have to go over it with. That being said, I hope you really enjoyed this conversation. Please comment down below if you have any questions, comments, or concerns. Thanks for watching. Take care and stay safe out there.